Okay, we have made a linear model, and we are really excited about our linear model, as we should be, because as I've said repeatedly, we have to love our model. So before we get too excited about sharing our model with the rest of the universe, what we're going to want to do is we're going to want to do a little quality control on our model. We're going to want to make sure that we are actually happy with how our model is performing when it comes to the underlying assumptions of the model. Now, hopefully before we started building a model, we looked at a handful of the assumptions that we know should probably be there, which is, we'd like our covariates or our predictors to be normally distributed. And in this case here, with the simple linear regression, we would really like for our response variable to be normally distributed. And again, we want it to be normally distributed because we're going to be doing things like estimating the mean and the standard deviation. And we would like the mean to mean what we want the mean to mean. So we're going to do that up front type of quality control. But then after we build our model, we want to see how well our model is basically agreeing with the assumptions underlying our model. And a really important assumption of linear models, there's two in general that are pretty darn important. The first one is that we expect that the residual variation, so all the leftover variation, should be normally distributed. We would like that because that's what we're explicitly modeling, is our uncertainty is being normally distributed. And then the second thing, which people maybe don't think about as much, is what's called homogeneity of variances. And that refers to the fact that we would like our variance to not steadily increase as we increase the value of our predictor. We'd like the variance to be constant across the range of our model. And actually the homogeneity of variance is a much more important assumption to always remember, because it turns out ANOVA and these types of linear models are actually pretty robust to deviations from normality, but they're not nearly as robust from deviations from homogeneity of variances. So let's say that we've done our model, the one that we've been playing with, and what I'm going to walk you through is just the various steps of doing quality control, something that you're always going to want to do after you do a linear model. So I'm going to run through it once really quickly with the data that we've been playing with, and then I'm going to just simulate some data with a little bit of a larger data set for us to look at, just so you can get a better idea of what we expect our quality control steps to look like if we're going to stay super happy and enthusiastic about our model. So let me make myself small again. Seems to be the theme here. Notice that I'm in my office today. That's why I'm wearing a hat. It's freezing in my office. Okay, I just disappeared. Where did I go? There I am. I got to float on top. I got to float on top. Float on top. Thank you. All right, I'm floating on top now. Great. Okay, so we have our model, and this is the same model that we were playing with before, right? There's our model. There's our intercept. There's our slope. We've already talked about that to death, right? And again, we can do an ANOVA on our model, and then we can walk away and say, yes, nitrogen is an important predictor for height, so the best model that we have on hand right now is one where height is predicted by the amount of nitrogen. And I think that we were explaining roughly 46 or 47% of the variation by doing that. And so the first thing that we could do, which we already did earlier in the other video, is just to simply look at a histogram of our residuals. Again, we would really like for those residuals to be normally distributed, so I will say hist and model $residuals, because that's one of the things that's in that list. And we run that, and we get something that looks like this. And again, we only have 10 data points, so it's really hard to make an assessment as to whether or not that is normal or not. But it looks like most of the mass is in the middle, and again, there's only 10 things here that we're trying to make a histogram of, so maybe it's not going to be the most reliable thing to look at. If we were really motivated, we could use the normal test on our residuals, $residuals, and I do that. And using the Shapiro-Wilk test, I accept the null hypothesis that our data are normally distributed. And as I pointed out before, I couldn't even use my favorite D'Agostino test because you need at least 20 observations in order to even run that test. So okay, that would be the first step, is you could just look at a histogram of the residuals. What we can use, though, is we can also use some built-in functionality to R to do this quality control step. And maybe some of you have done this and wondered, what the heck was all this stuff that it's getting me? But I have that object called model. And if I were to type plot model, if I were to do that, the first thing it's going to tell me here, it's going to prompt me, hit return to see the next plot. And of course I'd like to see the next plot. I haven't even seen the first plot yet. So I go ahead and let me make my little plotting area a little bit bigger here. And the first thing it's going to give me is a plot that's going to show me the residuals versus the fitted values. And so the fitted values are, again, those are the values that are right on that regression line. And here that's shown as this dotted line. And all of these distances from the fitted value to the actual value here, that is the residual, right? That's the part of the variation that our model is failing to capture. And so when you plot out the fitted values versus the residual values, what you'd like to see is no pattern. You'd like to see just kind of just a scattering of plots where there's no obvious pattern, where the residuals are getting maybe larger as the fitted values are getting larger, or vice versa. You don't want to have a situation where at the lower values of the fitted values you have really high residuals, and then your residuals start to decrease. And so what you want to do when you look at this plot is just to see, I don't think that there's much of a pattern. So the red line that is there, that's just R trying to help you out to kind of draw your eye to any pattern you might see. And again, we only have 10 points here, so it's going to be really hard to actually see a pattern, which is why we're going to revisit this with a bigger data set. R will also always flag the 3 most extreme values. Just because R is showing you those extreme values doesn't mean that they're wrong. R is just trying to help you out, saying, here are the 3 most extreme values, meaning that those are samples 2, 4, and 9. Those were the values where the fitted value was furthest away from the actual value. So they had the largest residual value. So that's all it's doing. So we look at that and we're like, okay, there doesn't seem to be any super obvious pattern. So then we see here that it's saying hit return to see the next plot. Well, okay, I like the first one so much, let's do it. Second plot. Second plot is a quantile by quantile plot. We've already talked about quantile by quantile plots when we talked about normality test. And so what we have down here is we have the theoretical quantiles of where we expect our residuals to fall, assuming that our residuals are normally distributed. And here we have our actual residuals. And again, they're going to be standardized. They're going to be standardized because these theoretical quantiles are going to be based upon a standard normal distribution, which again is a normal distribution with a standard deviation of 1 and a mean of 0. And so we look at that, and if our residuals are actually normally distributed, we would expect all of these dots to fall right on that dotted line. That would mean that our residuals are matching our theoretical expectations quite nicely, and these are all pretty darn close to that dotted line. And so I would feel pretty happy. This is just a second line of evidence. We looked at the residuals versus the fitted values plot, and now we're looking at a QQ plot. Different way to kind of talk about the same thing. We look at that. Those all look to be following that dotted line pretty nicely. So okay, I'm pretty happy with what the QQ plot is telling me. Again, R is just pointing out that 2, 4, and 9 are those most extreme values. Doesn't mean that they're wrong. R is just helping you out to let you know what those most extreme values is. R. Okay, hit return to see next plot. Yeah, I like the first 2. Let's see what the third one has in store. The third one. So the third one is another way of looking at the first one, essentially. Except here, everything, the standardized residuals have been all made positive. So it's the absolute value, the square root of the absolute value of the residuals versus the fitted values. And so this is basically showing us the same information that we got 2 plots back, except here residuals can be positive or negative, whereas with the third plot, they're standardized, so they're in units of standard deviations, and it's the absolute value. And so if all of our fitted values were nearly identical to the observed values, all of those dots would be down here close to 0, because they would be really close to the expected value, the fitted values. But what we do is we can look at this, and again, this red line is just here to help kind of draw your eye to any kind of pattern that might be there. We only have 10 data points, so we really have to take that with a little bit of a grain of salt. But there's no obvious pattern. It's not like the residuals are getting larger consistently as the fitted values get larger, or they're not getting smaller, or there's not a real obvious hump in the middle. If there was a really obvious hump in the middle, that would mean that we have way more variance in the middle of our distribution compared to the ends of our distribution compared to what we would expect. So that's just a different way to look at the same thing. And then next we can say, ooh, hit return for the next plot. And this will be the fourth plot that it'll give us, and this will be the last plot that it'll give us. And what this last plot is going to show us is if there's any important problems that have to do with what's called leverage. And the idea behind leverage is that you might have extreme values that might drive the overall slope of that is part of your model. And so you can literally think about it as leverage. So if you have a really extreme value, you could kind of think about that as pulling up the line more than you would want to. And so what leverage is telling you is how important are extreme values, and are those extreme values driving the show? Because if they are driving the show, that's a problem, because you want to have a model that's describing your entire sample as opposed to being totally driven by one particular observation. And a general rule of thumb to deal with this is to use this thing called Cook's distance. And Cook's distance is a measure of the amount of leverage that's going on with your model. And in a general sense, we would like all of our data to fall less than 0.5 Cook's distance. And so here we can see our 9th value is right on the cusp, which means that our 9th value, whatever that is, that might have a disproportionately large impact on our slope estimate. So that's maybe something that we want to keep an eye on. If your leverage is above 1, that means that you have really, really serious problems, and you're going to have to consider either a different kind of modeling strategy, maybe check and double check and make sure that there isn't some kind of a transformation that you can do to get that extreme value under control a little bit. You definitely want to be concerned if your Cook's distance exceeds 1. And so what we'd really like is for all of our data to be between these two red lines. And again, even our 9th value for our small data set here, maybe that's something that we decide is something that we should be concerned about. So what I'm going to do is I'm going to run through these again, but I'm going to increase our sample, because I've said a couple of times where it's kind of hard to get an idea of what's going on if we only have 10 samples. So I'm going to simulate data where I'm going to have 100 samples. And so I'm going to cut and paste the code here. This is definitely code you don't need to worry about. This code is on the handout that you all have if you're curious to see how we're simulating these data. But here I've simulated data where I have nitrogen and I have plant height again. And I have, here's all of the data points now. So we have a lot more than 10. Actually, we have 90 more than 10, because I've simulated it so that we have 100 data points. Where am I? Yes. Yeah, okay. I'm gonna shoot through those. That's not what I meant to do, because what I want to do is I'm gonna put them all onto one plot so we can look at them all at the same time. So I'm gonna call up my friend the quartz window so I can make it big. And then I'm gonna use a graphical parameter. I'm gonna say par, and then I'm gonna use a argument called mfro, and that's gonna tell R how many rows and how many columns I want. I want 2 rows and 2 columns. So now that's going to pull up a quartz window, 2 rows, 2 columns. There's my quartz window hiding there. And then I'll go ahead and I'm going to plot out all of those things. And so here they all are. Here's the 4 plots that plot will give us. And so here we have residuals versus fitted. Again, there's no obvious pattern. We feel pretty good about that. At least I feel pretty good about that. There's no obvious upswing or downswing in the residuals versus the fitted. You can see that that red line now is hugging pretty nicely the 0 line, and that is where our actual fitted values would be in our model. We look at the QQ plot. Those points are following that dotted line really nicely. It really looks like our residuals are fitting nicely with the theoretical expectation of them being drawn from a normal distribution. This plot down here on the lower left, again, that's just a different way to show this plot, except here everything is on the positive side. It's the square root of the absolute value of the standardized residuals. And again, what we would like here is there to be no pattern. And if we look at this red line, that red line looks pretty horizontal. So I am really not worried at all about there being any kind of residuals or individuals that I'm concerned about. And then over here we have our residuals versus leverage. And all of our points seem to be well within that Cook's distance of 0.5. And so I feel pretty good. You're always going to feel better about a model the more data that you have. Having only 10 observations was great for our purposes when we were kind of just playing around with thinking about how these linear models are built. But it's always a little sketchy to put too much faith in a regression that is only based on 10 observations. There is no magic number of the right number of observations, and yes, it is totally possible to use only 10 observations, and it's not wrong, but there's just going to be a lot more room for you to maybe miss aspects of quality control that if you have a larger sample, you won't miss. And so what I'm going to do next is I'm going to change up the data a little bit, just so that way we are clearly violating some of the assumptions of the model. And so I'm going to go ahead and I'm going to close my Quartz window. And again, all this code is in the code that I've given you. And so let's say that this is our data now. We have nitrogen in parts per million, and then we have height. And that is a really big height, but who knows what units we measured it in? Maybe it was in microns. Okay, fine, Jim, it's microns, whatever you say. And so we can look at this data, and right when we start looking at this data, it's like, yeah, that seems to be a little weird. And we could even make a histogram of our heights here. So I'm going to say, give me a hist of our heights, and we look at that. And so even before we put together a linear model, we would look at that and say, I don't think that is terribly normal. And then you could explore some transformations and say, let's take a log transformation. Let's see if that looks better. Yes, that looks a lot better. That looks a lot normal-ish. And so really, in reality, what we would do at this point is we would just log transform our height data and then proceed and make a linear model. But for our purposes here, let's pretend that we forgot to do that. And it's not going to be until after we did all the work that we're going to discover that maybe we screwed something up. And so we have a linear model. I'm going to go ahead and I'm going to make a linear model based upon our new data. Okay, and here's our model. We have parameter estimates for our model. We could even do an ANOVA on that if we wanted to see how significant it was. Ooh, it's very significant. So we feel great. We're ready to tell the whole world about how great our model is. But this is where it's important that we do that one little step of quality control, which is to see whether or not the assumptions that are implied in our model are actually being met. So again, the first thing we could do is we could look at the histogram of the residuals of our model. Residuals. Hist. Yeah, we really want those residuals to be normal. And again, that does not look normal. So there's our first red flag that maybe we have some quality control problems. And now let's go ahead and let's go through those 4 plots again, just so we can see what those diagnostics look like when we've clearly kind of screwed up a little bit and violated the assumptions of the model. So I'm going to pull up that window again, that Quartz window, and I'm going to say plot my new model here. And what do we got here? Well, now you can see, looking at the residuals and fitted, that there's clearly a problem here, right? There's a pattern where the residuals are getting a lot kind of larger as we increase our fitted values. That is definitely a pattern. That should concern us. If we look at the QQ plot, again, we'd like all of these dots to fall right, or all of our data to fall right on this dotted line, because that would be our observed residuals versus the theoretical expectation if it was from a normal distribution. And we eyeball that, and yeah, there's a problem there, right? Because we've really gone off the rails over here, and it's no longer following this dotted line closely. So there's red flag number 3, I guess. Like, we got problems. If we look at our scale and our location, which again is just a different way to look at this plot, again we see that it's going up as we increase the fitted values, and there's this kind of big mess of an increase in the variance in the middle, and so that's going to tell us, yeah, that's potentially a problem. And then finally we can look at the Cook's distance, and you can see that there's this one little nasty data point here that's almost up at 1, that's really bad land. Anything above 0.5 is potentially a problem, but once you get to 1, that's a serious problem. And so based upon our quality control of looking at the histogram of our residuals and then looking at the diagnostics that R is happily providing for us, we eyeball that and we say, we have some serious problems. We need to go back to our data and understand why we're having those problems. And again, we would discover that we have that problem because our data are clearly not normally distributed. And so again, this is, if you had done all this at the front end, then we would have been probably fine and happy with our quality control diagnostics. But because we didn't do that, we didn't learn about it until the end, that our data does not meet the assumptions of our model, which means that we really can't trust our model all that much. Okay, so that's what those diagnostic plots are. Get in the habit of always doing diagnostics. Whenever you build a linear model, you want to make sure that you feel as good about your linear model as you want to feel good about it. Regardless, you have to love it because it's your model. But yeah, let's make sure that you're meeting those assumptions. And that's the general quality control. And there's one last caveat with quality control. And this